Thank you very much for inviting me. I know Sharif University is the top university in Iran, so I feel very privileged to get invited. And I have colleagues from Iran, some students around me, so I know that yeah, so you are really the best program. So this work is a recent work is still under review and revision. So I would really appreciate if you have any questions, feedback, comments. So feel free to interrupt me at any time during my presentation. And yes, as Dr. Habibi said, this is I'm Wei from McGill University, but now I'm actually in China, traveling, spending some time with my family. And this is joint work with my colleagues Yuli Zhang and Ningwei Zhang, both from Beijing Institute of Technology. So let me start with just a little introduction about my research. So I consider myself as doing something about smart city operations, and this is an emerging area with a lot of scholars joining this emerging area. So it's a very broad area, and in my opinion, what are the elements of smart city operations? So if you look at this pyramid, at the bottom, our cities have infrastructures for sure, right? And on top of that, based on those infrastructures, they provide some services to urban developers. And those services need to reflect some values that we cherish, right? So they can be very broad. So at my research scope, in terms of infrastructures, I look at electricity, transportation, and also some water infrastructures. I look at the services like mobility, energy, and the retail logistics in our cities, and especially how those services they are interconnected with each other, like the talk I'm going to present today. So more often, the transportation, energy, and retail they used to be separate from each other, but now they are getting more and more interconnected, coupled with each other. So that's very cool. And also we look at efficiency, sustainability, equity, inclusiveness, etc. So all these values, all this stuff, thinking, I create a lot of research opportunities. So I really hope that some of you can also join this stream of research. Okay, so now let's start. Let me start with some motivation about this work. We all know that electric vehicles are booming around the world. I'm not very familiar about the situation in Iran, but at least in North America and here in China, it's really a big thing. About 2 years ago, the sales of new cars, there were only like 2.7% of new car sales were electric, but this number will be about 58% by the year of 2040. It means that more than half of the new cars will be electric. So this is really amazing, right? So this is really driven by a lot of government regulation, a lot of environmental concerns, etc. So it's really going to be the future. And that means that there are going to be more than 5 million electric vehicles on the roads in the world by the year 2040, a big number. So then the question is how to refuel our electric vehicles. There are mainly two ways. The primary mode is called plug-in charging, right? So you just park your car somewhere, and you plug in the charger to your car, so that it takes like at least 30 minutes or a couple of hours to get the battery charged. So this is in contrast with an emerging new mode called battery swapping. Actually, I took this picture, and actually I was literally at this battery swapping station 3 years ago. I was standing there chatting with someone, and I witnessed how fast it was to using this battery swapping mode to change a battery. So it took less than 2 minutes actually. Basically, the idea is, for example, this is a taxi car, and it moves into this station, and there is a robot take taking out the battery from the bottom of the car and replace a new one, the charged battery. So the whole process was super fast. And now it can be even faster. So actually, last Friday I visited another company of doing battery swapping. Their latest technology can enable 20-second battery swapping. So it's super fast, even much faster than the refueling gas. Because of this swiftness, because of the speed of battery swapping, the battery swapping station can be very small, right? Compared with this plug-in charging station, right? Because you don't really need much space. And another advantage is safety, right? You don't, as the car owner, you don't have to necessarily own the battery. The battery belongs to some professional people. They can take care of batteries. So it's safer, and it means that the car can be cheaper, right? You don't have to own a battery. So with all these advantages of battery swapping, we used to learn that it was not a success in the past 10 years, actually, especially in the Western world. Some people tried this idea of battery swapping, but they failed. But over the past 3 years, China has been taking the lead to promote this battery swapping modes. And several Chinese companies, such as BAIC, based in Beijing, and NIO is it's like a Tesla in China, based in Shanghai. So they are very ambitious promoting this battery swapping mode. For example, this company plans to invest a big amount of money to build at least 3,000 battery swapping stations in China by the end of this year. And Neil once offered his car owners like a free service of battery swapping for their whole life. But this service was very expensive. They no longer offered this service. So I really regret I didn't buy a car at that moment. But this is going to be the trend. So let me give you a little more about the history of battery swapping. As I said, in the past 20 years, the adoption of battery swapping was not a success. Some people tried this idea. For example, Better Place, the company, they burned a lot of cash. Eventually, they went bankrupt because it really takes a lot of money to to have an initial layout of battery swapping stations along some freeway network, right? It takes a lot of money, but on the other hand, the customers they wait, they won't buy a car until they do see a mature network of swapping stations on the road, right? So this is really a chicken leg dilemma, and many companies try it and failed. But this is no longer a problem now because for two reasons. First, especially in China, money is not an issue in many cases. You know, the Chinese government is very centralized government. I guess the same thing in Iran. They are very ambitious. They just give you a lot of money, a lot of subsidies, a lot of incentives to foster this business model. So money is not an issue. And second, the batteries now, thanks to the technology advancements, batteries are now much bigger. So the range anxiety was no longer an issue. So customers can drive their electric vehicles to travel a long way. So these two effects make the adoption issue no longer a problem. So I call them like a phase one challenges. So this is already the history. But now some new problems arise. There are some new issues. I call them the phase two challenges, which are ongoing. What are they? So those are the challenges about scaling up battery swapping services in our cities. We no longer worry about adoption. We no longer worry about the initial chicken egg dilemma, but think about some other issues like proximity, right? Suppose you live in a big city like in Iran or in China, you really want the battery swapping stations to be close to your home or your workplace, just like the gas stations, right? But the price you pay of having such a station proximity is that you really have to run a big network of battery swapping stations. And such a highly decentralized network of swapping stations is difficult to operate, right? We are doing operations research. It's difficult to run highly decentralized the system. And second, batteries availability is another headache. You don't want to have a lot of battery swapping stations, but without batteries there, right? So in order to guarantee some service level, you really have to stock a lot of batteries in your stations. And we know that the batteries are expensive, and the batteries are not environmentally friendly. It's very painful um, to to dispose and recycle batteries. Right? It's a lot of environmental concerns. So we really want to minimize the stock of batteries. And third one was not really realized until recently. When our ancestors planned the modern urban grids, the distribution power grids, they never anticipate that there will be so much need, charging need. There will be so much electrical load of charging batteries, right? So the grid capacity is a big concern now. If you have a lot of batteries that need to be charged, the urban power grids will be overloaded. So that's another big concern. And this is a big problem, especially in developing countries or even in Western countries, like in United States or Canada. They no longer government no longer spend money on updating their infrastructure. The Joe Biden and administration is trying to do that, but people typically don't consider upgrading their urban grids. Even in China, this is the power grid of Beijing. So those thick lines, they're okay. They're like a high voltage power transmission lines. They're strong. But if you really go to the center of the city, you look at the circles, those are like 10 kilovolts substations. If you really want to go beyond, go to local communities, the local power grid cannot afford having too much battery charging needs, battery charging power. So this is really a severe constraint. So how to solve this problem? How to satisfy? Uh, how to address these challenges? Some people propose this idea. So the biggest grid company in China called the State Grid Corporation of China, they proposed such an idea. How about we swap locally and charge centrally? For example, suppose this is a city. Those circles represent the local swapping stations so that they are close to your homes, right? But because of the grid's capacity constraint, they ship the swapped batteries to some centralized charging stations represented by those rectangles. So, and look at this the diagram. Basically, suppose I have a car with battery swapping. Then I will drive to a local swapping station near my house and switch out the depleted battery and get a new one. And once there are a lot of depleted batteries in the swapping station, the swapping station will make a call to the centralized charging station, and the truck will ship those newly charged batteries to the swapping station and pick up all those depleted batteries. So this is the idea. So this ongoing work is to address these phase two challenges by studying this swap locally, charge centrally system. So this is like a new form of urban infrastructure. It's quite new, and so we really want to have gain more understanding about it. And so the goal of this paper is do some data analysis, develop some modeling, and to how to run the system, where to locate those centralized charging stations, and the resulting problem is very difficult to solve. So we propose some solution algorithms, and then I will present some insights. So basically, the model I'm going to present is a joint location in the inventory model. At the operational level, I try to model the inventory operations of this swap locally and charge centrally system. On top of that, I want to develop a facility location problem to not to deploy those local swapping stations, but to deploy those centralized charging stations. So if any questions, please feel free to text me and or just speak up. So this work is related to some literature, but to my knowledge, the literature is quite scarce about battery swapping. There are a few papers published in Management Science and Amazon, but they're mainly about the phase one challenge, about adoption. But here we're looking at how to scale up battery swapping services in our cities. This swap locally, charge centrally idea was also explored by some engineering people, published in IEEE, etc. But their models are very simple, deterministic model. So we do believe we as operations research scholars can contribute some interesting models and insights. Our model is also reminiscent of some classic repairable inventory theory, and I will explain that later in a few slides. So fortunately, we got some data to support our research, and we got data from National Electric Vehicle Supervision and Management Center of China. From there we got a lot of records of real-time electric vehicle operations, and we identified more than 8,000 battery swaps in Beijing in December 2019, and this is like a aggregate hourly demand profile. So these are the peak hours, and those are like off-peak hours. One thing interesting is that we realized those battery swap arrivals are not necessarily poisson. Sometimes they can become non-poisson. So we cannot simply assume those are poisson arrivals. Okay, so next, let's look at the setup of this problem. Again, so imagine this is a city. We have local swapping stations represented by circles. They are served by some centralized charging stations represented by those rectangles. We assume that each swapping station independently follows an RQ policy. In case you didn't learn this policy before, the idea is very simple. Suppose I am the swapping station. Every time the inventory level of the charged batteries drops below R, small r, I want to make a call and order Q batteries from a centralized charging station. Okay, so that is the RQ policy. In the meantime, for each charging station, I want to decide how many batteries I need to stock before the operation starts, right? I need to have some initial stock level to satisfy some initial demand. And then I want to charge batteries, ship batteries, receive new batteries, etc. to circulate. So to circulate all the batteries. So this represents a complicated multi-echelon repairable inventory system. We really want to model this system. So first, let's look at those swapping stations. Those local swapping stations. So here this still is like a warm up. It's very simple. Suppose that the arrivals is a renewal process. Up to time t, there are ns battery swaps that have arrived. If you want to set up some stock service levels such that I want to make sure that the stock out probability is no greater than epsilon s, meaning that, like, for example, I want to make sure that 95% of the time when the driver arrives at a swapping station, he can find a available battery there. Okay, so if you set up such a chance constraints and approximate the arrivals using some normal distribution, suppose we know that the hourly demand has a mean as mu and variance as sigma square, then we can easily express the reorder point R of the swapping station. That is small r. So this is like the mean demand, and this part is like a little bit of safety stock. So this idea is very simple. I want to set up some safety stock to make sure that I can satisfy the customer demands most of the time. What's more challenging is the operations at those centralized charging stations. We want to apply the same simple trick, right? To use some normal distribution to approximate the demand, but it turns out it's very complicated. So we model the counting process of battery deficits at a charging station. with respect to each swapping station. So what is that? So basically, we consider a stochastic process called the battery deficit. It's nothing but a difference between battery expenditure and battery income. By battery expenditure, I mean the total number of batteries that the charging station has provided to a swapping station up to time t. It's like you're spending your batteries to someone else. So this expenditure minus battery income. So this is a number of batteries that are high have received and also fully charged up to time t. Okay, so this is like the number of batteries that have earned up to time t. The difference is the battery deficit. So if you want to, again, ensure some service level, let's call it epsilon c, so that, let's say, for example, 95% of the time, when a swapping station calls the centralized charging station, I want to make sure that the centralized charging station have enough batteries to ship to the swapping station. I want this probability to be high enough. Okay, so I wanted to apply the same trick of approximating this battery deficits sum over all swapping stations to using some normal random variable. But this is not, it's not, it doesn't help. The key issue, the key challenge is that, so recall that these operations, they're all in batches. They're not continuous. Trucks carry batteries in batches. So this D is not a continuous variable. It's like a somehow discretized. So it's using directly using normal distribution is not a good idea. So it took us 2 months. I and my co-authors, we got stuck there for 2 months. We tried to prove, we tried to derive, tried all directions, and eventually we were lucky. And I, I just want to quickly show that, yeah, we did some math work, and eventually we're able to these are really main results. So analytically categorize the mean and the variance of battery deficits based on those lemmas. So the first part is that the mean of the battery deficits at a charging station can be expressed using this closed form expression. Okay, so the mean battery deficit is it's proportional to the transportation time and order quantity. This is still not quite, this is not difficult. This is a challenging part. After a lot of effort, we are able to derive a very close, very precise approximation of the variance of the battery deficit. It turns out that this variance can be approximated by a piecewise function. When the order quantity, so Q is the order quantity, each time how much batteries a swapping station orders. When the Q is very large, then this variance is a linear function of Q. Okay? But when the Q is very small, suppose that each batch is so those are small batches, then this variance is a quadratic function of battery order quantity. It's like Q squared. This is quite interesting. So that means that we really need to be careful about order quantities. And we did some numerical experiments to show that the approximation is super precise. Those red dots represents our approximation. You see, they're super close to the true value. Okay, so thanks to this closed form analytical expression, we're now able to approximate the battery deficits, and then derive the stock level at centralized charging stations, capital R. So this is, again, the structure is still similar to the classical one, right? This part is a mean demand. This part is mean demand, and this part is the safety stock. You need to stock some extra number of batteries in addition to the mean demand to hedge against those best uncertainties. So basically, this entire term represents how R represents how many batteries you need to have initially at a centralized charging station. So in addition, we also derive some benchmark the model. For example, the battery charging are on site at central and decentralized swapping stations for comparison purposes. Okay, so this is really the main results we have. But we after we got a round of feedback from reviewers from Memory Science, and they give us a lot of comments, very helpful comments. So we also derive a lot of other results. And for example, thanks to the reviewers' comments, we realized that this system is so close to the classical repairable inventory system. Think about it. In our paper, we consider a swap locally, charge centrally network, right? And in the literature, if you go to literature in 1980s or even 1970s, there are a lot of papers about multi-echelon inventory systems with batched repairable items. So they're very similar, right? The batteries are just our analogy of repairable items. The centralized charging stations, they are just like a repair depot. And local swapping stations, they are just like a repair basis, considering those classic papers. So then we ask ourselves, what are our contributions? We realize that, yes, we made quite a few contributions. We're very happy. So first, we allow the order quantities and transit times to be heterogeneous across different swapping stations, whereas in the literature, they assume that those queue, order quantities, and transportation times, they're all the same. Okay, so this is one generalization we made. Second, whereas the literature approximate this batch arrival process using some Poisson process, we can more accurately model this batched arrival process using some advanced queuing modeling. For the sake of time, I don't want to show all the queuing analysis. If you're interested, you can go to our paper posted in SSRN website. And thirdly, we're very excited about this new results. We are able to analyze the random charging times or random repair times. Even and this random times, so basically the number of time, basically like how many minutes you need to charge a battery. So this number can be random across different batches, and they can also be within each batch. So this is also another big extension, a big generalization of the classical literature. So these are some technical results we derive, but I don't want to show that too much details in this 1 hour talk. But we have everything written in our paper posted in our website. Okay, so we have finished modeling this inventory system, right? How to run this decentralized swapping stations, how to run the centralized charging stations. Then our second question is how to locate where to deploy those centralized charging stations. We assume that those local swapping stations, they're easy to build. In China, basically one of the biggest petroleum companies in China, Sinopec, the partners with those battery swapping service operators, so that they can co-locate battery swapping stations with their existing gas gas stations. So it's not a big issue. But where to locate centralized charging stations? That's still a big problem. That's an open question. So here's our facility location model. Our locations include ZH indicates whether to deploy a centralized charging station at location H or not. Y is a assignment decision. YIH is 1 if I want to assign swapping station I to be served by a centralized charging station at H. Okay, so these two are both binary variables. And Q, so far I haven't talked about the order quantity. So here I want to jointly optimize the order quantities. along with those location decisions. So this is the object function. So this is like a swapping cost, station building cost, charging station building cost. Those are like the battery cost. We call that we need to have a lot of batteries in our system. And this is the transportation cost of transporting batteries between swapping stations and charging stations. So the main headache is that if you plug our previous results into these terms, you realize that this term is non-convex. Why is non-convex? Because remember, this phi of q is the piecewise variance expression that we derived. That was piecewise, and that is after you place this square root, it becomes non-convex. So this problem cannot be readily solved by some commercial solvers like Groby or Cplex. So this is really a headache. So and also please notice that the Q decision only appears in these terms, right? So I really want to somehow get rid of these annoying terms involving Q, and there are piecewise non-convex, right? This is really non-piecewise. So here's the idea. We propose a solution algorithm. And the first step is really to package all those terms concerning Q to a function called G. Okay, so basically G here is a subproblem. It is a minimization problem over order quantity Q. Okay, and second, we realize that this G function is a function of Q, but it's also a function of the assignments, the Y decisions. Okay, um, sorry, it's not a function of Q. Actually, it's a minimization problem over Q. So it's only a function of S, where S is like it's a set function, but it also can be considered as a function of our Y decisions, the assignment decisions. And this set function turns out to be submodular. So that's why we can have they have some nice properties. Once the set function is a submodular function, although it is a nonlinear function, we can express this, we can approximate this function using a simple as a linear function, right? So this g function can be expressed by a linear function of y variables. And the coefficients of those y variables are nothing but those like the marginal cost. The cost of adding one more swapping station to be served by the charging station. Those are like a marginal cost. So if you knew the y's, we can quickly recover the original nonlinear function. But the problem is that before solving the problem, we don't know what are the y's, what are the optimal y variables. If you don't know the optimal y variables, you can get a lower bound of the g function, the original g function. So basically, we can use a simple linear expression to approximate, to lower bound this original g function, but it's much, much simpler, the form, right? So that is the idea. And with this idea, we can reformulate the original problem. We relax a little bit so that we introduce a new variable called w. W represents the g function. And in addition, this w is lower bounded by this linear function. So now everything is linear, right? Everything is linear. But the price we pay is that there are an exponential number of such functions, such constraints, because we really need to consider all those permutations of y variables. So our idea is that instead of including all those exponentially many constraints, we start with just a subset of those constraints and keep solving this relaxed problem. And along the process, we can get a lower bound of the optimal object value. And we can also easily construct some feasible solution so as to get an upper bound solution. So basically the process is that we keep adding constraints like this. It's called a constraint generation algorithm. We keep adding constraints, keep adding those cuts, and we keep getting tighter and tighter lower bounds as well as upper bounds until the lower bound, when lower bound and upper bound they're close enough, we know that we can solve the problem. Okay, so this is the idea of the constraint generation. The main idea is that the subproblem is submodular. All right. On top of that, we also need to consider derive some efficient algorithm to solve this subproblem. Although the master problem can be solved by the constraint generation algorithm, during the process we need to solve a lot of times this subproblem. Although this is a continuous problem, right? The only involved Q variable. There's no integers, but it's still annoying, right? It's a non-convex and piecewise. I really don't want to solve. I really want to have some smart way of solving this problem efficiently. That's why we derive a parameter search algorithm. I don't have time to talk about the details, but the idea is in the following. So look at this nonlinear ugly format, right? How about if I'm able to find a proper theta is a parameter. If I can find the right value of theta, then these two problems they're equivalent. By equivalent, I mean that the optimal solution to this easy problem, this parameterized problem, you see this is much easier than this one. The optimal solution to this problem is identical to the optimal solution to this problem if I have a right value of theta. Because this is the idea. So then the problem boils down to iteratively finding the best theta value and solving this easier problem. Okay, and this problem turns out to be super fast to solve. Basically, it is an iterative process using some branch and bound procedure. Let me skip that. And we can quickly solve this parameterized problem because it's just a just like it looks like this. Actually we don't have to solve it. We can just use some existing formulas to get a value of Q, and we iteratively update Q and theta, and then Q and then theta until we know that we got optimal solution to the original problem. We also derive some modules to speed up this algorithm. So this is the whole idea. So basically, the entire solution algorithm is a combination of a constraint generation module, which solves the master level problem, and a parameter search module, which helps speed up the solving the subproblem of this one. So this is the whole idea of solving this problem. Okay, so I have talked about how to model this swap locally, charge centrally system. I've talked about how we solve this facility location problem using some algorithms. Then let's look at some insights we can obtain from our analysis. We first calibrate our model using some real data. Our data have multiple sources. We talk to some practitioners, those car manufacturers and equipment of battery swapping facilities, and they kindly provided us with some cost parameters, and we also have data, as I said, from a very cool national data center to get the real-time operations of battery swapping from customers. So we gotta have demand, we have parameter values, and we also have a lot of cost information to calibrate our model. Okay. If you're interested, you can feel free to cite those numbers we have. So then we first test the computational efficiency of our algorithm. We want to see whether our algorithm works well or not. So first we test the effectiveness of our parameter search module, solving the subproblem. So those numbers highlighted is the time it takes mean time it takes to solve a problem instance using our algorithm. So they're in milliseconds, right? Super fast. Whereas if you use Groby, you see for the problem with 90 swapping stations, the Groby will take 370 seconds. That is not tolerable because we need to solve this subproblem numerous times. during the entire solution procedure. So this is too much. And also, please notice that, recall that this problem is non-convex. We cheated here a little bit in the sense that we only consider the convex part of the problem to let Groby solve. Okay, so without helping Groby could not even solve this problem at all. So it means that our algorithm is super effective. The second, what about the entire solution algorithm, including both constraint generation and parameter search? So again, those numbers are the time it takes to solve our problem using our algorithm. Even for big problem size with 90 swapping stations, our algorithm is able to solve the problem on average within 7 seconds, right? Whereas the Groby simply fails, even if we help the Groby by convexifying the problem. So it shows that our algorithm is not only necessary but also efficient. All right, so then let's talk about some insights. So what can we learn from this? Is it really a good? So basically, the question is it really a good idea to have a swap locally and charge centrally system? How is that compared with the conventional on-site battery swapping system? So let's first look at the left panel. The vertical axis is the cost, and the horizontal axis is the demand of scale. So I increase the demands from left to the right. So let's first focus on two curves. The blue curve represents the main scenario, the swap locally, charge centrally scenario. And this curve, the dashed dotted line with circles represents the traditional scenario, the benchmark. All right. So with on-site battery swapping. So it turns out that our new infrastructure is more expensive, right? The blue curve is above the black curve. And also similarly, this on the right, the vertical axis, the batteries you need, how many batteries you need. Again, our new infrastructure is lost to the traditional system, again, represented by this line. So at this moment, we got disappointed, right? After so much work, so much efforts of modeling and solving this problem, our system sucks. Our system was beaten by the traditional problems. And what's the point of considering this problem, right? So we were puzzled a little bit here, and it turns out yes, this is why this is the case. So here are some insights we learned. Indeed, the centralized chart is less scalable, less cost efficient than decentralized on-site charging, if all else being equal. So we were surprised by we study our textbook. We know that by centralizing some charging demands, we should enjoy some pooling effect, right? Why after centralizing batteries charging, it becomes worse? So we were puzzled. So the reason is that yes, indeed, there is still exists some favorable pooling effect. It's still good to pool your battery charging demands at some centralized places. However, this favorable effect is dominated by two unfavorable effects. Okay, so the first unfavorable effect is the order batching effect. With this centralized battery charging, you really have to batch those batteries into batches and have trucks move them to somewhere else to charge. So this batching and the transportation takes time, the transportation lead time. So this batching effect, this transportation lead time effect, they're both bad, right? They're both bad for our operations. So they amplifies the uncertainty of the system. They amplify the uncertainty of demand. So the overall effect is actually unfavorable. The overall effect is not good. The traditional system is better. So we were very disappointed, frustrated. So what's the point? Then the second observation saved us. It turns out that remember that one of the main motivations of this work is that on-site battery charging may not be feasible because our urban power grid is capacitated. We simply do not have enough capacity to charge those batteries on site. So, if we instead assume that at local places, because of the capacity limits, we can only charge those batteries using small charging power, slow charging basically. Then this curve represents that scenario, the slow charging scenario. All of a sudden, you see that the observation is reversed. Now, both the cost and the number of batteries we need in the slow charging scenario are much, much, much higher than the system, the blue curve with centralized charging. So it shows that if our urban grid is capacitated, then it is definitely better. It's necessary to consolidate your charging need at some centralized charging places where you can get access to fast charging. So this is our main message of this paper. Okay, so finally, our final observation is that this system is pretty robust against some parameter uncertainties. So but the idea is that suppose this is optimal solution somewhere here, I can deviate from the optimal solution in terms of both order quantity and where to locate your charging stations. Okay, so if I won't lose too much by moving away from the optimal solution. So this is helpful, right? Because in a city, our cities are complex. You cannot build charging stations exactly where you want, right? So sometimes we have to compromise with other complexities. Also, by lowering the order quantities, actually I can reduce this red line shows that I can reduce the number of batteries I need. So by paying a little bit more, so the red curve represents the case with smaller order quantity. I pay a little bit more cost in exchange for a considerable amount of battery reduction. Okay, so that's good, right? I care about the planet. I want to maintain a smaller battery stock level. Okay, so quick summary. So in this work, we study a new urban infrastructure. It's called a swap locally and charge centrally system. We really want to enable a large-scale adoption of battery swapping services. And we develop models of battery stocking, charging, and circulating. Then we propose a location model. We solve the model by developing some algorithm. Then our main message is that if our urban grid is really capacitated, please, we need to consider some centralized places to charge our batteries. Okay, so I think this is the last slide. If you're really interested in this line of research about electric vehicles operations, or more broadly about smart city operations, I hope you can browse my website. I have some recent works about either like autonomous electric vehicles, urban microgrids, or autonomous vehicles for selling products in our urban open spaces, not only for ride sharing, but also for supporting our urban grids. So I think there are a lot of interesting research questions awaiting us, and in terms of how to smartly couple the energy systems and transportation systems in our cities. With that, thank you very much.